We're going to let the x approach a, and what are we looking at? We're looking at that slope, right? That's the slope formula. All we're doing is taking the limit of it, if this limit exists. We have seen limits in this class not exist, right? Yeah. So as long as this limit exists and you get a number, then that tells us that the slope of the tangent line should be whatever that limit is approaching. That's it. I mean, that's it. That's what the calculus is right there. It's just the limit in that formula. Well, but the limit, remember, gets as close as you ever want to get, right? So there's this property of the real numbers, and this, I don't want to go like we did the other day with stars and stuff like we were talking, but there's a property of the real numbers that says that if you have numbers that are converging to something, like getting closer and closer, it can only go to one thing. Like you can't have convergence to a number and then it go to two places. So it's called the completeness axiom of the real number system, that you got only one number you can go to. So even though the limit never actually gets us there, we know it's headed to something and we know that that thing is never going to change. So that should be the true slope, whatever it is, right? Whatever the number turns out to be. All right. So let me see here. I think we're ready for the final version, right? We got our 2 points. This is getting old. Drag it, drop it, boom. But now we don't have the problem anymore, right? We have a tangent line because we're going to do a limit. And here it is. That's the slope formula I just put over. No, I erased it. This is the formula for the slope of the tangent line. It's a limit, right? And then from that, we can get the equation of the tangent line, which is that same equation we just had on the board a second ago. Do y'all see that that's the same exact equation? Y minus y1 equals m times x minus x1, right? All I've done is I've replaced this. I've added the limit into it. And so now this is no longer the slope of the secant line. This is the slope of the tangent line. All right, I want to just recap one more time. Give me a function. I don't care what it is, right? Give me a point to start at, A. If I want to know the slope of the tangent line at that point, then what I'm going to do is calculate, well, I can leave it up here. This right here, this limit would give me the slope of the tangent line at that point. Then if I want the equation, I just plug everything into this formula and I have the actual equation of the line. I think it's time we do an example, right? We've got all the formulas. Let's do an example. This works for any function, right? Any function. So what do you say we start simple? Yeah? Let's start with like the most basic function we can think of that's not like too basic. How about like x squared? All right, let's let f of x be equal to x squared. Part A, I want us to find the slope of the tangent line at x equals 4. Let's go 2, sorry. Let's go 2. That number's going to be too big. Let's go with 2. And then part B, I want us to find the equation of the tangent line at x equals 2. The hardest part of this problem, the calculus part of this problem, is part A. Because part A requires a limit, doesn't it? If I want the slope of a tangent line, I need a limit. So for us in this problem, here's my work. For part A, right, what's A for us? What's the anchor point? You know, we're looking at the graph. Here's x squared, like this, right? And we are going to an x value, excuse me, of 2, right? Right there. That's my anchor point. So that's the A. The A is the 2 that I'm starting at. And then I'm going to pick a second point that's, I don't know, it could be to the left or right. I'm just going to pick a second point over here. Right, and that's my other point. I'll do it in blue, right? And what I'm doing is I'm drawing a line through those, and then I'm going to move this x towards that A, right? I'm going to move this x over. So using this formula, the slope of the tangent line is the limit as x approaches a of f of x minus f of a over x minus a, right? That's our generic formula for any function. We're just going to plug things in now. We're going to plug and chug. What did I say a was? 2. Everywhere I see a, I replace with 2. Limit x approaches 2. F of x. What is f of x? What is the function's value at x? It's x squared, isn't it? I mean, that's the function, right? X squared. So I'm going to replace that top left corner with x squared minus f of a, which is really f of 2. So what's the value of the function at 2? That's a 2, right? So let me do something because it's the first example. I'm going to go a little slower. I'm going to rewrite the formula. Let me just replace all of the a's with 2's first. I'm going a little too fast there. Okay, so I replaced that with 2, that with 2, that with 2. Now let's talk about what each of these things are. Okay, this is x squared minus 2 goes into the function. 2 squared is 4. And then over x minus 2 is x minus 2. Y'all see where everything's coming from here? No one has questions? Are you sure?
Yeah.
Yes?
Can you re-explain like that part?
What top part?
The x squared minus 4.
Okay, so this right here, right? This right here is just the function. So what function did I give you? X squared, right? So I'm just replacing that with x squared. Now, this one, f of 2, is what you would get if you plug 2 into this, right? If I ask you to plug in 2, you square it, you get 4. Got it? So that's your 4. And then the bottom is just x minus a. That's from this formula. That's just x minus 2. Yeah? All right, everything's plugged in? Yes? Okay, now try to take the limit. What happens? X is going to 2, you get 2 squared, 4. 4 minus 4, 0. 2 minus 2, 0. 0 over 0? Careful. In a limit, 0 over 0 for us means what? Bad. Bad what? Do some algebra, right? Do some algebra. You see? This is the whole reason we studied limits in chapter 1, is because we are now doing a limit where we're getting this thing of 0 over 0, right? So now we bring in the algebra. Yeah, what algebra are you gonna use there? Difference of squares on top. So this is gonna be equal to limit. See, I'm not dropping the limit yet. I'm just doing algebra. The top is difference of squares, x plus 2x minus 2. And the bottom is x minus 2, right? And I can cancel those factors x minus 2 so long as I promise you that x is never 2, right? Right? So now I'll substitute. But I'm going to just write it one more time before I substitute. Everything went away except x plus 2. And now just let x go to 2, and you get what? 4. This is the slope of the tangent line at that point. That's the slope of that line, okay? I've answered part A. Part B says what's the equation, right? What is the equation? So for part B, I want to find the equation, right, of the tangent. Line at x equals 2. So I'm going to use that formula, y minus f of a equals the slope at x of the slope times x minus a. Right, that's our generic kind of formula. But for us, a was 2, so I just replace, well, what is this? Do we know this? Yes. What is it? 4. We just did all that work, right, to get 4. So that answer right there, that 4, right, this 4 is coming from here, right? We know that's the slope of the tangent line. And then the rest of it, we're just plugging in, replacing the a with 2. We did this earlier, didn't we? That was 4. Yeah. I'm going to distribute here. Distribute the 4 through. You know what I should do before? No, I'm not going to distribute. Hold on. Let's just leave it right here like this. That answer right there is acceptable. That is the equation of a line, right? And that is correct. Like, that is it. You're done here. However, in college algebra, most of the time when we write the equation of a line, we get it like solved for y. We try and get y by itself. So I'm going to go ahead and do that, although on a test I'd be happy, completely happy with this answer. So to actually take this and solve it for y, I'd have to distribute the 4 through the right side. And then what? Add 4 to both sides. So what would your final answer be here? 4x minus 4. There you go. Is that the equation of a line?
Yes.
Yes. All right.
So on the test, you could do either.
Yeah, this is, especially if we have fractions, this is, just leave it here. All right, I want to see if we can put this all together geometrically. All right, so I'm going to go to Desmos. What I'm going to start with here in Desmos, I'm going to leave that equation right there. What I'm going to start with in Desmos is the original function, right? The original function was f of x equals x squared. There's the original function, right? And we were interested with what was happening at a was 2, right? So I'm going to plot that point on my graph. A is 2. So that's the point 2, 4. Right? See that point there? I'll even label it for you. There's the point 2, 4, right? And I was trying to find two things, the slope of the tangent line here and then the equation of it. Do you all agree that the slope of the tangent line there should be at least positive, right? Do you all see? I mean, it should be positive, and it's pretty steep. So I think it's 4. But the best way to check to see if we got it is just to now have Desmos graph this. And when I graph that, what I should see is a line that passes through that point and is tangent, right? So let me graph it. There it is. Okay? So we have achieved the goal, right? We have found the equation of the line that is tangent to this curve at that point. Understand what we're doing? All right, let's do another one.
Were you able to use a calculator on the test?
For what part? Like graphing or? I mean, you could use your calculator, absolutely. I know coming from like high school, calculators are like the thing, you know, and everyone goes to the calculator to do a lot of that. Here in this class, there's very little need for calculators other than to help you with arithmetic. So when I give a test and I see a student just sitting there like 70% of the time on their calculator, to me, that there's a huge disconnect then, that the student's not getting, that this class is not about punching into a calculator. It's about understanding concepts and putting it all together without the technology. Look, I mean, if we could use technology, then why are we doing anything we're doing here, right? Like, I mean, Desmos can actually do this. Watch, check this out. No, I won't show you right now. I'll show you it later. But I mean, Desmos can do all the work we just did without anything, right? You can go to a different software and type things in. It'll just give you this answer, just like that. So that begs the question, why are we doing this, right? Like, if we have the technology, why are we doing this? It's a good question. Do you all have an answer? I don't have an answer. No, I have an answer. You just won't like it, I don't think. Do we care to go down that road? So I'll give you a quick story. When I was in school, I was a math major, right? Not initially. I was architecture at first, then mechanical engineering, then physics, then math. That was my journey, right? Okay. So, but in my upper division, like junior, senior level course, I took this course called numerical analysis. And the project for the semester, we had to all do a project, was to find some software, okay? Like, there's all sorts of software out there. We had to find software that was used by engineers or, just in the STEM field. We had to find 2 different pieces of software. And what we had to do was basically feed the software problem. So imagine this is the computer, right? So I'd feed the problem to the software, right? Feed it in there and have the software give me an answer. And the goal of the project was for me to be able to take this problem and solve it theoretically or like purely solve it by hand, like show what the answer is. And then put the problem through here and get an answer that wasn't correct. So in other words, I had to exploit the weaknesses of the code. Like whoever coded the program, I had to actually look at it, find some weakness, and then exploit it, right? And so that it would give me incorrect answers. The only way a person would know that answer is wrong is if they understood the theory behind it, right? The theory. So at what point do we as a society disconnect ourselves from the theory and rely completely on the technology, right? Like if we come into a calculus class and all I do is use technology to do all this, then who's left that actually understands what's going on? Does that make sense to you? So at the end of the day, this calculus course is in the sequence of classes that a math major would take. So math majors have to see this, right? Like we have to still grind out the math by hand. It's kind of like when you take an art class, right? You have to go through like, art history or something. You always have to kind of like cover what's been done and not ever lose roots of the actual mechanical thinking, right? So anyways, that's my little argument. This is still a math class, not an applied math class where all we do is do computers. I wish we could do that. That'd be a cool class. Calculus just for fun. Let's use technology, right? You don't get credit for it, but we just use technology. All right, let's do another example. Let's let f of x be equal to the square root of x. We're going to keep this with relatively nice functions. Part A, find, I'm just going to put m tan just to save myself from writing. Slope of tangent line at, let's go with x equals 9. And then for part B, find the equation of the tangent line at x equals 9. I'm just abbreviating because time and... That's the same 2 questions, right? All right, if I mess up your name, please correct me. Zeta? All right, Zeta. I said that okay? All right, Zeta, what now?
You can plug in the 9. Oh, for the equation, so you would do as a limit of x approaches 9.
Okay, so you're ready, you're using the formula. Can you give me the formula you're about to use? Okay, perfect. So we're using just the formula for this, right? So if you like formulas, we're using formulas, right? And then you said, I think you had already done that, but then you did what?
You would plug in the 9.
Plug in 9 for A. Okay, A, so that's 9 there. F of x stays f of x. F of A becomes f of 9. And then x minus the A becomes 9. You all agree? Okay, thank you, Zeta. David. Okay, David. I'm thinking that I did not call on the people I'm calling on right now, I did not call on last time. So if I've called on you before, I apologize. All right, David. Can you tell me, David, what's this?
F of x.
Mm-hmm. So what is it for us in this problem? What's f of x?
That's the tangent.
No, just this right here. Just this right here. What is the function I have provided you for this particular example?
Oh, okay, 9.
Nope. The function.
Oh, the function of square root of x.
Square root of x. Okay, so that top left corner is always going to be the function that we're talking about for this particular problem. So let's continue. Limit x goes to 9. We're going to stick with you. Okay, minus. Now, what's f of 9? So what happens if you plug 9 into that function?
You'll get
3. Okay. Everyone good? All right, now x minus 9 on the bottom is just x minus 9. We're not changing anything there. Is that all right? All right, Isaiah. Where's Isaiah? All right, Isaiah, there you are. What happens, Isaiah, if I let x go to 9? What happens up top?
3 minus 3.
0 over 0. 0 over 0. And when we talk about limits, 0 over 0 is, you've got to do some algebra trick, right? You got to do some sort, we got to do something now, right? We got to do something. We do not at this point say undefined or does not exist. This is why we're here, right? This is what separates the algebra from the calculus. We actually have something to do now. All right, so I'll stick with you, Isaiah. If you want any ideas of what, I mean, you have to figure out what to do with this, some sort of algebra. Is there anything kind of like pop into your head when you see this? What's it? Hold on. Conjugate, right? Why? Why did you think conjugate? Yeah, root, right? So we said when we see roots, think conjugate. So I'm going to come in with a conjugate. So here's what it's going to be. Equals limit. See, my limit's not going away. Still here. Okay, I've got root x minus 3 over x minus 9. I'm going to multiply that times 1, right? 1. This is a 1, but it's a very clever one. It's the conjugate. It's root x plus 3 over root x plus 3. Is it guaranteed that this is going to work? Is there a guarantee that that's going to work? No, but conjugates, that's what we try, right? We got to try something. Anybody have any questions over what I just did? Isaiah's driving the bus here, so if we go off a cliff, it'll be on you. No, it's going to work. Okay, good. All right, Christopher. All right, you following? Everything good? Okay, so help me out with the top here. Here to here. So when you put the two roots, multiply them. You're just doing like root x times itself, right? So you're squaring it. And the square and the root kill each other off, right? Just x. Okay? Just x. What about the middle multiplications? They're going to cancel, right? So I don't even have to worry about those. So all that's left here is that, which is minus 9, right? Good. So the top is just x minus 9. And I'm extremely happy to see that, right? Because the denominator has an x minus 9 as well, and that's the part that was causing the division by 0. So I told you earlier, last week, don't multiply this out. Do not. Leave it alone. So on the bottom, I still have the x minus 9 in parentheses times the root x plus 3, like that. And now your x minus 9s can cancel out, or reduce, right? Technically, it's called reduction, reducing, but we all like to say cancel. Just don't forget there's a 1 up top, right? When you get rid of that factor on top, you still have a 1. And now I'm like one step away from taking this limit. Just going to clean it all up. I have a 1 on top. The only thing left on the bottom is the square root of x plus 3. And now I think I can do this without too much effort. Go in here, root 9 is 3, right? Root 9 is 3, 3 plus 3 is 6. So 1/6. That is the slope of the tangent line, right? That is just the slope of the tangent line. So I should expect, remember lines, this is a slope of 0, right? Positive slopes, negative slopes, right? The steeper it is, the bigger the number is, right? So a 1/6 slope is positive, but it's not very big. So I should expect just a little pitch to this line. But that's only the slope, right? Yes?
Could you also have done difference of squares in the
You could have done, I think I showed you all that in class as well, that there is a clever way that you could look at the x minus 9 as root x plus 3, root x minus 3, and then cancel immediately. I didn't want to do that. Because I think most people are going to think conjugate, but that works. All right, let's see. This is fun for me. Alana, Am I saying that? Yes, Alana? What am I going to do now, or what are you going to do now? I've got the slope of the tangent line. What's the next thing I'm looking for here?
Put in the equation.
Equation, right?
Yeah.
The equation. So now we want the equation.
So y minus 3.
Minus 3. So can we back up a little bit? Let's just do the formula first. You're doing good, but slope tangent line, x minus a. That's the formula, right? I called that m tan instead of m, but that is going to be the slope that we just got, right? And we're replacing all of our a's with 9. Okay, now I'll let you take over.
Y minus 3 equals 1.
Okay. Where'd you get the 3 from?
The square root of 9.
Yeah, because you plug 9 into the function. The original function was square root of x, so you get the 3 equals, what was the slope of tan?
1 over 6.
1 over 6, and then parentheses,
X minus 9.
x minus 9. Box it, we're done. While you're pondering that, I'm gonna use Desmos to verify. I'm gonna have Desmos graph the square root of x. The point we're looking at is 9, 3. There it is. Okay, oh, sorry. So the red, right? The red is the square root of x. There's the point 9, 3, and we're trying to find the slope of the tangent line there, or sorry, the equation of tangent line there. I'm going to type into Desmos exactly what I have there in the box. Y minus 3 equals 1/6, parentheses, x minus 9. There it is. See? We have found the equation of the line that goes through that point and is tangent to that curve. So do you see that we're actually using the idea of a limit to actually solve this problem now? This idea of derivative is saying, hey, we have a very special limit. This limit that involves that slope, right? The limit of that slope gives us the slope of the tangent line. All right. Let's do another one. I know some of you had me for pre-cal. It's been a little while, but do you remember me talking about turning the screws? Do you remember me talking about turning the screws? I must not have turned them enough then. Do you remember that? Turning the screws? No? Must not have been forceful enough with that idea. So what we're going to do is continue to turn the screws. The phrase turn the screws comes from medieval torture devices, right? Like you put your head in between two planks and then just start to turn until you admitted to something or converted to their God, right? You believe in our God? No, turn it more. You know what I mean? No? Basically, it just means problems are going to get harder, right? Things are going to get tougher, right? So we turn the screws. How much would you like me to turn? A little bit, a lot? You ready to go a lot? You ready for something harder?
Yeah.
Okay, let's go with it. So how about, let's do this function right here. I want the slope of the tangent line at x equals 1, and then the equation of the tangent line at x equals 1. Same two questions, right? Same two questions. Let's see who's up. Erica? There you are. How's it going, Erica? Okay, Erica, what, I don't know. Just tell me something. What do you want me to do? Part A. And give me the formula that you're going to use. Okay, good, that's the slope, but because it's the tangent, we need in front of it limit x approaches a. So by itself, that's not the tangent line. That makes it the tangent line. All right, Erica, what's a for us in this problem? 1, right? So go ahead and let's just rewrite this with 1s everywhere we see a's. X approaches 1, f of x minus f of 1 all over x minus 1. Do you all understand that every problem you could ever do, when you get this limit set up, it's always going to be 0 over 0? Do y'all understand that because you're moving that second point on top of the other one, you're always having 0 over 0? So it's always bad. You always need algebra, right? No matter what. Okay? I want to get through everyone today. Let's see. Alexander?
Yeah.
Okay. So you following everything, Alexander, up to this point? Yeah? Okay. Tell me what you want me to write next.
I just went ahead and did the limit x approaches 1 and then 1 over square root of x plus 3.
Okay, so you're just replacing the f of x with 1 over the square root of x plus 3. And then minus f of 1. So what happens, what does that give you? What does that mean? Oh shit, I just looked right into the projector. What does that mean? Plugging 1 into the function, right? What happens when you plug 1 into this? You get 1 over 2, right? 1 over 2, or 1 over the square root of 4. Right, so if I replace that with 1, that becomes 4. Square root of 4 is 2, 1/2. So the top right-hand corner of this is 1/2. Man, that was really bright. Not stars. I'm seeing rational numbers. No, I'm kidding. That was a good joke. Come on, you got to give it to me on that one. All right, x minus 1 on the bottom, right? We all good? All right, the next part, I'm not going to call on somebody. I'm going to ask for a volunteer because the next step is going to be the tricky one, trickiest part. This does give you 0 over 0. If you try right now, let x go to 1. This is going to become a 4. Square root of 4 is 2. 1/2 minus 1/2 is 0. 1 minus 1 is 0. We do have 0 over 0, right? So who has the algebra for us here? What's the algebra? So the conjugate will be involved for sure. But is that the first thing you want to do? Common denominator first. Now, I'm not saying that it won't work if I go conjugate right now, but if I did conjugate right now, it would have to be this plus that. And I promise it would be pretty ugly if we did it. Like the algebra would get kind of messy. So what I'm going to do first is put these two fractions together with a common denominator. Right? That's what I'm going to choose to do here. So conjugate's coming. Let me do it on a different line here. Man, that is really bright.